and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend. I'm your host, Dr. Moiya McTier, an astrophysicist, a folklorist, and a good friend to the universe. I think about the universe all the time. I am recording today from my office here at Pale Blue Podiversity, and I'm expecting a special guest. Julia Schifini is a podcaster, a voice actor, and a sound designer who hosts some of my personal favorite podcasts. I'm talking Spirits and Join the Party. Her submarine just docked a little bit ago to the Podiversity campus, so she should be here any minute now. Julia, come on in.
What I love about the campus is the fact that I can ride the submarine directly here. It's almost like the ferry in New York City, where it's like just right up to the gates, baby. It's great.
Yeah, it's actually a direct transfer from the ferry. You don't have to pay. It's like it carries over the $2.90.
That honestly, ideal. We should be doing that for every single service that we have in New York City, for sure, when it comes to public transport. We should be.
We should. I mean, I believe that public transport should be free.
Yes.
But yes.
Ideally.
Free transfers at the very least.
At the very least. We'll hopefully be getting free buses in the near future, but fingers crossed.
Fingers crossed. Come on, Zoran. Julia, how you doing? Is there anything else you would want people to know about you?
I love that I came in on a submarine. I am a sound designer as a sort of side job to podcasting. And one of my favorite shows I've ever sound designed for takes place on a submarine sort of subnautical base. And it is dealing with all different kinds of underwater prehistoric creatures. So that's called Primordial Deep if you ever want to check that out.
Definitely check that out. I will include a link in the show notes.
Ooh, thank you.
Yay. Thank you for being here. And I would love to get to know you a little bit better. I have some questions that I think will dive at the core of who you are as a person. Are you ready?
Yes, I'm so ready.
Excellent. The first question gets a little deep, so we can take a deep breath, a primordial deep breath. And then I would like to know, when you think about the universe, Julia, and like how big and vast it is, how do you feel inside?
I feel like the Calvin and Hobbes comic strip where he's standing outside at night with the cosmos above him and he goes, "I'm significant," screams the dust mite.
I've never seen that one. You just had that in your, right at the top of the head.
I think about it all the time.
Do you have any idea why?
I think that in some ways, the vastness of the universe is extremely overwhelming. There's a line in me, and I cannot remember what it is from right now, but it's like a fake meditation podcast, I think. And they're like, think about this. Too big, scale back. So that's how I feel a lot when I think about the universe.
Too big, scale back.
Too big, scale back.
Yeah, the astronomer trick is to just use scientific notation, so we don't actually have to think about how big it is. Yep. We just see the exponent and the number, and we're like, oh, it's 12 big.
But if you had to look at all those zeros, you'd be like, oh, too big, scale back.
Exactly. Yes, we have this little trick. It's the scientific notation.
Otherwise, I feel like I would be sort of like a Lovecraftian, the unknowable horrors of Lovecraft. That's how I feel about the universe sometimes.
Okay, well, I'm glad you've scaled back so you're not constantly overwhelmed. Okay, next question. Do you feel like your sun sign fits who you are as a person? Yes,
I am a Libra and therefore incredibly indecisive. Cannot make a decision to save my life.
Oh, no. Is that like the main trait of the Libra? What else?
It's about balance because we're the scales. So it's like, you're weighing a lot of different decisions, which is where the indecisiveness tends to come from. Also, a lot of people think that Libras, especially like femme-presenting Libras, are very like fashionable and flirty, and I don't get that vibe particularly, but I will take it as a compliment if someone sees me that way. Sure.
I see you as very fashionable.
Oh, thank you, Moiya. Yeah. That's so nice.
And I could imagine seeing flirtatiousness if we didn't have a professional friendship.
Yes, that's true. That is true. If I haven't been in a relationship for 16 years.
That too.
That too.
But no, you have a very welcoming presence.
Thank you. That's very kind of you to say.
This is a new question. Okay. I have not asked anyone this before, but it seemed like a good Julia question.
Hot and fresh just for me? Thank you.
Right off the presses. Julia, would you rather be a star, a moon, or a planet?
Oh. There's something really romantic about being a moon, I think. Mm-hmm. And as you know, I'm a mythology nerd in general. And so when I discovered for the first time that all of Jupiter's moons are named after his like mistresses and stuff like that, I was like, okay, yeah, that makes sense to me. And so I really like this romantic relationship of being in a orbiting relationship with someone or something. And also the like phases of the moon speaks to me in a way that feels distinctly who I am as a person, because I think I go through interesting phases and stuff like that, but I always return back to my own self.
Mm-hmm. Oh, I love that. So you are a moon.
I am a moon. Mm-hmm. I always joke that my mom is the moon in that sense that like the moon birthed me. So yeah, I think the moon.
I have had that a similar thought where when I was younger, I definitely would talk up at the moon as if it were my mom. Yeah. And I had this idea that the sun was like my dad.
Listen, I was an Artemis girly growing up, so yes. I had a particular kinship with the moon, I would say.
Same. Okay, that question went as well as I hoped.
Excellent. I'm glad I could be the testing ground for it. I think it was a great question.
What law of nature would you want to change if you could?
Oh, the preservation of matter.
Tell me more.
I think we should get rid of some shit.
Something should be able to disappear completely.
Exactly. I think we should raise the stakes on how matter is. I think some stuff should just go away.
Is this like after a certain time, like all matter should have a half-life, or?
No, I think just if like enough of us will it, things should just go away.
I like that.
I think it's vibes based.
Julia, I love that so much.
I'm not a scientist, in case anyone can't tell from this interview.
So what you're saying is we should amend the rules of the universe such that if enough of us get together and we're like, hey, we don't want air pollution anymore, it could just be gone.
Yeah.
Nice.
I like that.
I think
that's
too.
Great. I'm realizing it's a little bit like Thanos snap Avengers Endgame situation, and I feel a little bit bad about that, but
it's fine.
I think it's fun.
It's fun. That's why I paused when I was thinking of my example, because I didn't want to say people.
Yep.
Yeah.
I think we're all thinking of at least one person that they would want the universe to disappear, but hey, what can you do?
What can you do? Look, the universe is taking care of it for us. All things in their own time. Mm-hmm. Mm-hmm. Okay. I love that law change. That's so fun. I'm also thinking of like, if all of the other rules of physics stay the same, like what would the consequences of that be?
Don't think about it too hard.
It's my job to think about it too hard, Julia.
But I can't. I said the first thing that came to my brain. It was a first thought, best thought situation.
Yeah.
I don't want to think of the repercussions.
Okay. All right. No repercussions. I will think about the repercussions later. But I think that, look, just like a world building exercise, everything would turn out fine. We would make sure it's fine.
Yeah, there would be other changes that would be made in order to deal with the one that I just made for the universe.
Yes. The universe is very accommodating in that way. All right. Now, Julia, imagine we are sending you out into the universe as an astronaut. So you are in the rocket. We're about to launch, but you are in charge of the playlist. So what song do you want to play right as you blast off?
Don't Stop Me Now by Queen.
Great one. Mm-hmm. Great one. How did you know that so quickly?
I don't know. I was just like, what would like really get me excited about blasting off into the universe? A thing that probably I would be extremely anxious about. Mm-hmm. I think, one, the energy of Queen is perfect. And also, I think lyrically, that's just a great song to blast off the planet with.
Couldn't agree more. Yeah.
There we go.
I love it.
I am doing a lot of just like, normally I would think a lot more about these questions. Just right off the dome today.
Yes, right off the top. That's exactly what I'm looking for. Then to get us into our topic of today, which is telescopes, just in general, telescopes. Yes. Do you have a favorite telescope?
I don't. I don't know a ton about telescopes. I remember as a kid, I picked up a very, very simple, basic one at a garage sale one time. And so that was sort of my experience with telescopes and space. I did go to like, not space camp, but like a day camp that had it was a science day camp that had a space section to it, I guess. And I, again, loved the moons. I loved the constellations and stuff. But the actual like science aspect of it, I was like, take it or leave it. But I do remember that telescope and I have fond memories of it. So that one's my favorite.
Good. You know, it genuinely did not occur to me that you would pick that type of telescope.
A child's telescope, yes.
This is why it's so important for me to interact with non-astronomers.
I'm like, I know the Hubble, that's a thing, but I have more nostalgia for the telescope that I had that I would take out on full moons and go, oh, there it is.
Oh, yay. Yeah, I never had one of those telescopes.
Really?
Yeah, I did not get into astronomy because I loved stargazing or looking up at the night sky. I could not have cared less about it, genuinely, until I got to my sophomore year of college when a friend dragged me to an astronomy class to try out with her. And free pizza made me stay in the class. And by the end of the semester, I was like, oh, galaxies are interesting. But I don't stargaze. And if you gave me one of those types of telescopes, I could not operate it, actually.
It was, I would say, extremely simple. Not even the kind where, like, you look down and it reflects up. Again, physics is not my specialty, certainly. But it was one that almost looked like a non-collapsible version of what a pirate would have.
Like the spyglass type.
Yeah,
even that. Like, maybe a really basic one that isn't hooked up to electricity and it doesn't move or on its own or anything. I could look through a scope. But anything more advanced than that, actually beyond my capabilities, which surprises a lot of people.
You and 10-year-old Julia handshake emoji.
Hey. Okay, cool. Well, to teach you a little bit more about telescopes, so maybe you have a favorite by the end of this, I want to go into the history of how they even got here in the first place. I did an episode already about Galileo. I think it's episode 76. And so we definitely talked about telescopes in that episode. But Galileo isn't like the beginning of telescopes. So let's go back even further.
Yay, history.
History. Yeah, I thought you'd like this part.
I do.
So even into antiquity, we see evidence of people understanding that water and glass and other mediums can influence the direction of light. It can bend it one way or another. And some materials bend light more than others. Now, this is why we actually see evidence of like amber chunks or like glass chunks being used as reading stones, which is really nice. And we see reading stones from Islamic scholars starting in the 9th century and spectacles in Europe starting in 1300. So we had glasses in the 1200s, and it took another at least 3 centuries for people to realize, oh, hey, that glass stuff that makes us see better down here, maybe we could also use it to see better up there.
Yeah, maybe we could look at space instead of just on Earth.
Maybe, perhaps. And so it wasn't until 1608 that a spectacle maker in the Netherlands named Hans Lippershey invented, he didn't call it a spyglass, but like that collapsible pirate type thing, where you have a big, long tube, and on either end of the tube you have a lens of glass, and one lens kind of gathers the light and directs it towards your eyepiece. So there will be different types of lenses. And legend says that Hans Lippershey thought of this because there were 2 children playing in his spectacle making studio, shop, whatever you do. And he just happened to see 2 lenses line up with each other, and he noticed that the light passes through it differently. So that's probably not actually what happened, but that is the apocryphal story that we have had passed down by time. He filed a patent in 1608 with the Netherlands Patent Office, and they were like, oh, okay, this is cool. But then almost immediately after, a couple other people also submitted patents. So Lippershey never actually got the patent. The patent office was like, clearly this is too easy to reproduce, so it's not patentable.
Ah, okay. Yes, because it's presumably just 2 lenses and a tube. So,
exactly.
Yeah, I get it.
Yeah, but he did get a deal with the Dutch military to make spyglasses for them. And so really the connection between astronomy and the military-industrial complex goes back to as far as it can. Unfortunately,
that seems like it is the history of most technological advances, is like, I have an idea, and they're like, cool, how can we use it to kill people?
Right. Oh, let me give you a bunch of money to figure out how we can use it to kill people. that's what he did. But there were a couple other people who thought of this idea around the same time. One is Jacob Metius. These are all like Dutch people. And he applied...
I like that. What was happening in this area that everyone was just like, but what if we figured out telescopes?
It was a kind of headquarters or like a central hub for glass making.
Oh, okay.
Yeah.
That makes more sense than me being like, what happened in this one specific area?
Right. I'd say like Italy at the time, like especially I think this one little island called Murano had the biggest reputation for glass making. But
yeah, Murano glass. I have some in my house.
There you go. And that's where Galileo was when he got his lenses. But there were also a lot of glass makers and spectacle makers in the Netherlands. So Jacob Metius applied for the patent 3 weeks after Hans Lippershey, and then didn't get it. Another guy named Zacharias Janssen, which is a fun name.
So good.
He is credited by many with inventing the first microscope, because microscopes and telescopes, very similar technology when you look at it's just like glass lenses that will redirect light in a specific way.
One is down, one is up. Yeah.
Exactly. They both make small things look big. Except Zacharias Janssen claimed to have invented this, like he made the claim long after he actually invented it, like several years. He also might have been neighbors with Hans Lippershey. And so I think that it's like he saw his neighbor go to the patent office and he was like, wait, I've done something like that too. But there's even more like doubt around him because he had known run-ins with the law, some of which included like some fraudulent stuff. So his claim is just really dubious. But I think that shows that telescopes at their core are so basic, they're so simple that like multiple people came up with it at once.
Yeah, but also wild that it took so long for us to figure that out as well.
Yes, exactly. What do you mean? We had glasses already. Just look
we
up.
Couldn't do anything else with that glass at all.
Clearly not. Until Galileo. And as soon as he heard about Hans Lippershey's spyglass, which actually Hans Lippershey just called a looker in Dutch.
Yeah.
And so Galileo heard about these lookers from a friend writing a letter. News spread really slowly back then, in 1609. And he was in or around Venice, so he went to a lens crafter in Venice and got 2 lenses and then glued them to the ends of a tube and made the first telescope.
Woo! He did it.
Hey. And he saw beautiful things. He saw that the Milky Way was made up of individual stars. He saw craters and other features on the moon. He saw the phases of Venus. He saw star spots on the sun. Sunspots, I guess most would call them. He saw comets between us and the sun. So he opened humanity's eyes to the universe for the first time. But other people were definitely looking through their own rudimentary telescopes at the same time. They just didn't publish when he did. Or if they did publish, they interpreted the data they saw in a way that would be less offensive to the Catholic Church.
Ain't that just the way? Ain't that just the way?
Ain't it always? And yes, so he went against the church, ultimately was punished for it. And this whole story is the first chapter in the book that I'm writing right now, which is why I am doing this episode now, because when the episode comes out, I will have turned in my first complete draft of the book.
Heck yeah! Let's go!
Thanks, dude.
I also want to give a quick shout out to your episode on Galileo that you did on This Guy Sucked, which is also a show that I edit for Multitude. So
yes,
it's the best of all the worlds, not just both worlds, all the worlds.
I like that we overlap sometimes here at Multitude.
Yes. I think that makes a lot of sense. I find it fascinating that it was this kind of one area. It makes a lot of sense that it is in these sort of glass capitals of the world, or at least of the West. Was there any other non-Western technological advances besides the, I think you said there was an Arabic sort of looking glass thing?
The reading stone.
Yes, there was the like Arabic reading stones, but was there any other of the like proto-telescope in places besides the West?
Not ones where you look like far into the distance. It would have been technology that makes things near you just magnified. So the reading stones, you like didn't even hold them up by your eye. You like put them on the page.
Right.
And yeah.
Like a boomer in a dark restaurant.
Exactly like that. And so for thousands of years, humanity was just a bunch of boomers in a dark restaurant until the 1600s.
Fantastic. Thank you.
Great analogy. So now I'd like to talk about some important telescope terms. And I think the very first that we need to clear up is a refractor versus a reflector telescope.
Okay.
Have you heard of these terms before?
I have heard of them.
Great.
You might have to specify more about what they mean.
Actually, Julia, I was just planning on saying that and moving on completely.
Cool. Great. That makes sense. I was like, you know what? Sometimes I'll learn from context, and that's okay. You know, that's being an adult.
Yeah. No. I'll walk you through it.
Okay,
so
cool.
A refractor is what Galileo's telescope was. The idea is that you use lenses on the ends of a tube to bend and focus light towards your eyepiece. So you would have like a bigger lens at the end of the telescope that gathers light and bends it towards your eye at the end of that tube. Okay. These are a lot more common for amateur telescopes because making a huge lens is really expensive, so you're kind of limited in how big the telescope can be. And so probably the telescope that you used as a kid was a refractor telescope. And if you see anything that looks like a long tube, that is almost certainly a refractor telescope. There are other, pros and cons to them because of the shape of the lens used in the refractor. Like the color of the light that you get in the eyepiece is a little bit, we call it aberrated. Like the color is a little bit distorted because of the way the light bends through the glass. Like some colors of light don't bend as much as others, so you end up losing some of the light colors on the edges.
That's so interesting. I would have never thought about color changing because of the refraction. That's awesome.
Yeah, we call it chromatic aberration for anyone who wants to look up
cool.
more. Yeah.
That sounds like a D&D spell. Hell yeah.
Oh, it does. I'm going to put that in my back pocket for when I eventually host like a D&D campaign that's all based on space terms, but not set in space.
Yes. I love it.
So that's a refractor. And then the other type of telescope, broadly speaking, is a reflector. Instead of using lenses to focus the light, a reflector will use mirrors that are really strategically shaped and positioned to reflect the light that comes in from the sky up to some eyepiece or instrument. And these are most common for research astronomy because the mirrors can get really, really big, especially when you segment them kind of like a fly's eye. Like the JWST was segmented. It has all of those hexagon mirrors that together act as one big mirror.
Cool. I'm picturing how that makes sense in my brain, and I do get it, but extremely cool and not something I would have thought of as a thing that can really magnify. But I'm assuming it's because of the shape of the mirrors. That makes a lot of sense.
Yeah. And the telescopes that reflect in this way, they can have different shapes, and it really depends a lot on the wavelength you're observing. But essentially, the idea is you have like a bowl-shaped mirror.
Okay.
It's usually pretty, ever so slightly bowl-shaped, like one of those plates that you can also eat salad in. And,
Gotcha.
And that's sitting at the bottom. On top of that, high above it is basically an eyepiece. So the light will come in, it hits the bowl mirror at the bottom, and it all gets reflected back to that one point above it, like a triangle to the eyepiece.
I'm picturing the Death Star. Is that kind of the right shape? Like the bowl in the Death Star and then the laser that comes out of it?
I have to look up the Death Star.
Okay, sure.
Oh, like the one hole? Like the divot?
Yes.
Yeah.
And then when they shoot the laser out of it, it kind of looks like what you're describing with it comes up the bowl and then pinpoints into the laser that then destroys the planets.
Okay, yeah, I can see that. It also is very similar to a satellite dish. If you've seen there's the bowl of the dish and then there's that wire part that peaks on top of it. Yeah, like that.
Cool. Okay, awesome.
That's refractor versus reflector. Also kind of a tongue twister for the actors out there. And then another term you might hear often is aperture or diameter. This is the physical diameter of the collecting lens or the collecting mirror. The bigger your diameter is, the more light you can collect. So typically, the bigger your telescope, the better it is, but not always.
Sure. Okay. That makes sense.
Another thing you need to pay attention to with telescopes is angular resolution. This is kind of like the smallest angle that you can discern. Basically, it tells you how close can things be before you can tell that they are two objects instead of just one.
Oh, interesting.
Mm-hmm.
Okay.
Yeah.
Cool.
So you actually want a small angular resolution because that means things can be really close.
Mm-hmm.
And there is an equation that goes along with this. It has to do with the wavelength that you're observing in and the diameter of your telescope. And it's the wavelength divided by the diameter, which is why if you have a bigger telescope, your resolution is better because you're dividing by a bigger number.
That seems like such a simple equation, but I love when science is like just a little bit simple that you're like, of course that makes sense.
Yeah, it is. It's one of the first equations we learn in astronomy, like in optics stuff. Yeah, so there's angular resolution, and then there's focal length, which is especially important in refractor telescopes. The focal length is the distance between your objective lens, which is collecting all the light, and your eyepiece. A long focal length, so if your telescope tube is really long, that actually gives you a narrower field of vision. It's almost like squinting your eyes, and it really like focuses the light collecting power on a small area, which gives you just like a sharper focus there. On the flip side, a short focal length will give you a very wide field of view. So like our eyes, we can really think of our eyes as telescopes, as cameras. So our aperture for our eye is the size of our pupil, and that's like, I don't know, a few millimeters up to like a centimeter, maybe if you're in a really dark spot. So that's our aperture. And then our focal length is the distance between the surface of our eye and like the back of the retina where it gets processed.
Okay.
And that is about 2 centimeters, like on average. And so that's a pretty short focal length. And that gives us a very wide field of view. Like we have more than 180 degrees of vision, which is incredible.
Yeah. It's pretty cool.
It's pretty cool. Yeah. And that's how that works. You also have to think about integration time. Okay. How long are you letting light hit the telescope or hit your eye before you process that information?
Oh, okay.
For a telescope, and even for like a camera that you have on your phone, you can change the integration time or the exposure time. So you can say, leave the shutter open for 5 seconds, and it will collect 5 seconds of light and give you like a brighter image.
Gotcha.
Yeah.
Okay. I'm hearing a couple of like filmmaking things that I'm like, okay, so like aperture, I was like, oh, yes. Okay. I've heard of that before at least. And this is and I'm like, okay, these are making sense to me.
Yay. Yeah. I think if you have familiarity with film or cameras or anything, or if you like are very into how the eye works, telescopes are probably pretty intuitive for you.
Okay. Yeah, that makes sense.
Yeah. Do you have any idea what the integration time for the human eye is?
I think it's like longer than you think, right?
Yes, it is.
Yeah, because like, and also I know that like our brain, the image is actually like upside down and then we flip it in our brains. That's something that I do know about eyes and brains.
Yes. So it's different for the different type of light receptors that you have in your eye. We have rods, which are really good at like seeing motion and stuff, like seeing the amount of light. And then we have cones, which are really good at color and like that type of fine detail. And they have different integration times. But on average, it takes our eyes 1/10 of a second to like collect information before it can analyze the information.
Which is why like our reaction time to fast moving objects is sometimes like, just a beat slower than you would think it would be.
Yeah. And like it takes time for the neuron stuff to travel, but
we're going into spooky season now, Moiya, which is my favorite time of year. And so watching people react to scary things, like where there is that beat and then they react, is one of my favorite activities. So
okay, people watching during spooky season.
Watch your friends. Watch jump scares that you know are about to happen. Watch your friends go through haunted houses, and you'll see that kind of slightly slower reaction time.
It's because their eyes are integrating the light.
Yeah. And they don't know what they're seeing. And then all of a sudden, they're scared.
All of a sudden. Yeah, I have a very strong fight reflex, actually. So I'm not allowed to go to haunted houses. It sucks. I love Halloween.
Yeah, but sometimes you're going to do a punch, even though you shouldn't. So I feel you. I get it.
Please don't sneak up on me out in public. If you ever see me out in public, just approach with caution.
It'll be a bad time for everyone. Fair warning.
Fair warning, yeah. Hey there, friends. It's me. Julia found my collection of ethically sourced mermaid scales on my bookshelf. I find them down on the beach at the edge of campus, and I keep them. But I told her she could take some to make jewelry, so while she sorts through the jar, I'll share some messages with you. My first message is a thank you to all of my patrons. I couldn't make this show without you, so thank you so much. I also want to give a huge thank you and a special shout out to my sun-like stars, Scott Reynolds, Tom T., Nicole Bartlett, and Ashley Shambo. You are golden, and I hope that hydrogen that you are fusing tastes extra yummy today. If you would like to support this indie podcast on Patreon, you can hear your name on the show, make it to my patron star chart, and get research notes for most episodes for $5 a month at patreon.com/palebluepod. You can also make a one-time donation as a supernova at the PayPal link in the episode description. And of course, if you can't support us financially right now, I understand. I love you, and you're still space. The best way to help the show is actually to get more people listening to it. So if you want to take a link to an episode that you love and share it with a person you love, then you're just making more people friends to the universe, and you're helping out Pale Blue Pod. And I thank you in advance. Here's a reminder that Pale Blue Pod is a member show of Multitude, a collective of independent podcasts. And our collective is about to launch our annual multi-crew drive with a whole bunch of bonus podcast episodes. I actually just recorded yesterday a review of the movie Sinners, exclusively for the multi-crew, so be on the lookout for the drive. We're announcing details next week. Also, as a shameless plug, I would love it if you would please watch That's a Lot Show on Instagram, TikTok, or YouTube. The links are down in the episode description, and episode 7 is out this week. We are halfway through the season, and things are starting to get weird. I also have some exciting things going on behind the scenes here at Pale Blue Pod. I don't want to give too much away, but episode 151 will be very special, so stick around. And it looks like Julia has found a few scales that she can turn into a pair of earrings with a matching necklace. Oh, she's going to look stunning. But let's get back to this telescope conversation. Those are the terms. There's others that you're going to face if you have like a pixelated camera in your telescope versus others. Mm-hmm. But that really gets into the difference between telescopes and the things we put on them to analyze the light, which is an instrument. Okay. There's an important distinction. So the telescope is really just a light bucket. It collects photons. And that's useful information, especially in the 1600s when you've never collected photons like that before. But really, for our purposes of research these days, we need more information than just how much light is there coming at our telescope. And so we have built special machines that can comb through those photons and analyze them in interesting ways. The most obvious is an imager, so like a camera. And these days, a lot of the telescope cameras operate on charged coupled devices, CCDs. Okay. These are also the same types of arrays of pixels that you see in your phone or in digital cameras, where essentially they have an array of tiny little light buckets. They have an array of squares, which when a photon or an electron hits them, they react in a certain way, depending on how they're built. But it is a way of turning those electromagnetic signals into bits of data that we can run calculations on.
Gotcha. Okay. Interesting. Yeah. And I imagine that in terms of the instruments that we are using with telescopes, the imager is probably the one that most people know the most about, because when you think telescope, you think, oh, I get to see a picture of a planet that's far away.
Yeah. Yeah, okay, but telescopes will have, some telescopes will have multiple imagers on them because they'll be imaging in different regions of the electromagnetic spectrum, or they'll be in the same part of the spectrum, but with different pixel sizes. So like if you have, imagine if you have a grid that's like 5 square inches, but one grid has 100 pixels and another has 300, that 300 pixel one is giving you like much better resolution.
In my mind, it's like those videos that you'll see on like TikTok or Instagram where it's like, here's an image of an eye that I drew in 30 seconds, and here's one that I did for 30 minutes.
Yes.
Gotcha.
Yeah. Thank you for coming in with these rock star comparisons.
I'm doing my best out here. I'm trying to be the best layman I can.
You're doing it great. And imagers are really important because a lot of astronomy funding comes through public engagement and public excitement about the pictures. So
yes, exactly. Yeah. So that's how people engage with it. And, you know, when the public is more excited about space, they want to fund more stuff about space.
Yes, yes. And actually, there are a few examples of telescopes where we didn't need an imager on them. That's not the information we were looking for. But we put an imager on them because we knew it would get the public excited.
Yep.
Yeah.
But I love that, too, because as a non-scientist, as a person, however, who loves science fiction, who loves anything that is like set in space, I want to see the pictures of those cool planets and those cool galaxies and the things that I'll probably never get to see with my own eyes. But the fact that we can see them is so exciting in its own right.
Yeah. And we're such a visual species. I think that is how we're going to best feel connected to something else. Like, you got to see it to believe it.
Heck yeah.
But that's just imagers. I'd say most of the data that I've worked with has not been image data. The two other like major types of instruments that you'll see are spectrometers, which will take light in, split it up into all of the different wavelengths, and measure the strength of light at each wavelength. So you get like a graph of the strength of light over the electromagnetic spectrum. And then the other type is a magnetometer, which will measure the strength and the direction, like the position of a magnetic field. And you can do that, like, we kind of have to be near the magnetic field, but Earth's magnetic field and the sun's magnetic field, like, they extend so far. So even in a space-based telescope, you can still measure Earth's magnetic field.
That was going to be my question, which was like, are we trying to measure the magnetic fields of very far away planets like Neptune or something like that? Or are we just kind of doing the more local ones? Because I couldn't imagine reading magnetic fields so far away.
Yeah, you do kind of have to be near it. So to measure Neptune's magnetic field, we had to send a telescope out there to do it. But even then, magnetic fields overlap. So even when you're out at Neptune, you're experiencing Neptune's magnetic field and some of its moons' magnetic fields maybe, and the sun's magnetic field still. So these magnetometers can, especially because it can tell you the orientation of the magnetic field, it can help you tease apart which field you're reading.
Interesting. That's very cool. I think I knew that we were sending telescopes into space, but it didn't register to me that, like, you know, we're sending them so far. I don't know. That might sound a little silly in like comparison, but
no, that's not silly. Yeah, we have sent a few missions out there. The Voyager spacecrafts have since left the solar system, but we like sent them out ostensibly to study the planets in the outer solar system. And then once they completed that mission, we just let them keep going.
You know what it is? I think when I thought probe, I didn't also think telescope. And that's on me for not knowing that would be the things that obviously we're sending something out there to do stuff. And of course, they would also include telescopes.
Yeah.
But that's just me. I think I heard probe and I didn't think telescope.
That is fascinating. Okay.
Yeah.
Okay. Well, in my next section, I think I might be expanding your idea of what telescopes are. Okay. So I have some telescope superlatives for you. I have the biggest, the oldest, the most expensive, and the wackiest. And I'm excited to teach you about the wackiest.
Great.
The biggest telescope in the world is the FAST telescope in China. It stands for the 500-meter aperture spherical telescope. It's not a sphere. They lied.
They lied.
They really did. It's a big bowl. It is nearly 4,500 individually controlled panels on the mirror of this reflector telescope. But when I say mirror, don't picture like a shiny piece of glass that you could actually see your reflection in. This is a mirror for radio light because it's a radio telescope. So it doesn't look reflective to us. It looks like really gross side of a building sheeting, actually. Like it's dirt. Like I haven't been to FAST, but I've walked on radio dishes and they're not gross. They're gross.
I am now picturing the Sphere in Las Vegas, but as a giant telescope.
That's what it should have been.
I think that'd be cool. It should have been. Probably would have been better for everyone, but what can you do?
What can you do now? So yeah, they control each of these panels individually across 500 meters, and that is how they keep the shape of the dish relevant to whatever they're trying to observe, because they can't steer the dish. It's so big, it's just like sitting on the ground, staring up at what's above it. But by creating tiny shifts in the individual panels, you might be able to like point in one particular direction.
Gotcha.
Its primary goal is to study pulsars, which are like the cores of old dead stars that are they spin really fast and they have bright lights coming out of them.
Cool. Sounds fun.
It does sound fun. Yeah, pulsars are cool.
Moiya, I have maybe a silly question.
I bet it's not.
So I feel like I'm like in 8th grade trying to understand space again. Okay. Imagine you are at this, the FAST telescope.
Okay.
It is in China. You are looking at a very specific pulsar out into the universe. The Earth rotates. Do they only get a certain amount of time each day that they can spend looking at that pulsar?
Yes.
Okay, good. I thought that was like a silly question, but then I was like, but of course it has to face the thing that they're looking at, so they can only look at it for however long it's within its radius, I guess.
Yep.
Okay.
Yeah.
Wow.
It can pretty much see like almost half of the sky at once. Like it basically
Sure.
sees everything above it. And so it would take several hours for the pulsar to not be in its path. But yeah, it just has to work with the rotation of the Earth.
Yeah, that makes total sense. It felt very silly saying it, but logically it made sense to me, so I had to say it out loud.
I'm glad you did. Yeah, your logic was spot on.
Great. Good to know.
That's the biggest telescope in the world.
Okay.
The oldest working research telescope in the world was a little bit harder to find, but it seems like it might possibly be the U.S. Naval Observatory's Great Equatorial Refractor. It had its first light in 1873. That's when it took its first observation. And it's 26 inches across. So it's a lens that is 26 inches. For 10 years, it was the biggest refractor telescope in the world. Or at least in the U.S.
That's neat.
Yeah, and it was used to find Mars's moons, Phobos and Deimos.
Aw, that's really nice. Shout out.
Shout out to Phobos and Deimos. It is still used for research. There are obviously older telescopes, but they're not used for research. Like Harvard's 15-inch refractor is older than this, and students still use it. But it's for like Harvard's astronomy club. Like they don't do it for research.
It's just for funsies.
Yeah, for like funsies and outreach. And so a lot of the older telescopes are still used for outreach and public education, which is really nice, but not research.
I really like that, though, because I think there is something very nostalgic about, and I'm sure we'll talk about this a little bit later, but there's something really nostalgic about like rich guy who was super into astronomy and so in his house built an observatory.
Yes, there were so many of that. One of the fathers of radio astronomy, Carl Jansky, he literally just built a radio telescope in like his backyard.
Yeah. This is a aside, Moiya, but if you'll indulge me for a moment, this past weekend I stumbled upon a historic house. I'm on Long Island, and so the Vanderbilts had many estates on Long Island, and they turned a lot of them into museums. And there's a particular one that is on the North Shore of Long Island that is the home of William Kissam Vanderbilt II. And I kept saying to my husband, to be so rich and also to have a scientific special interest. Because we walked in there and I'm like, this is just a room that is filled with just marine specimens that he had taken over like 40 years of like just traveling across the world. Like he famously went to the Galapagos Islands and like took a bunch of specimens around the world. He had a like real interest in like starfish and different types of crustaceans and everything like that. So there was just an entire room full of just like bleached out crustaceans that were from his original collection. We saw a mummy that day too. It was wild. But my point being is we have so much of this nostalgia of like rich guy really was into science and we've preserved all of his specimens. And I love that that is still a nostalgic thing that we have for early astronomy as well.
Yes. Yeah. Wait, I really want to go to that museum now.
Anytime you want to come out, Moiya, we'll go. It's great.
Okay,
and there's
cool.
a great taco place. It's like 10 minutes from there. I'll take you.
Let's do it.
Heck yeah.
Okay, so that's possibly the oldest telescope. The
Cool.
most expensive, very easy to find. Do you have any idea what it might be, Julia?
Is it the most recent one that they made? I can't remember the name of it, but it's a bunch of letters.
Yeah. JWST
That
launched
one.
on Christmas of 2021 after being built for almost 20 years, and it cost 9.5 billion green American dollars.
You know what? The fact that you didn't say trillion is the most surprising part to me, personally. But hey, what are you going to do?
Honestly, if the government ever gave $1 trillion for a telescope, I would be like, well, that's greed. That's too much. But also, like, we like science. That's good.
Yeah. I mean, there are places that I would take money from to give to science, certainly, when it comes to my taxes. But
yeah, for sure. But yeah, unequivocally the most expensive.
yeah, and that's still a lot of money.
Still a lot of money.
Honestly, though, that's not as much money as I would think over the course of 20 years. You know what I mean?
Oh.
Because if you spread it out, that is less than $1 billion every year.
You're right.
It's only $500 million every year.
You're right. Yeah. However, we have built and launched and operated other space telescopes for less than that, like for $500 million total.
That's true.
So
that
it's
is true.
fine. Look, origami on telescope scales, very expensive. That's what JWST had to do. It was folded in such an intricate way to fit into the rocket, and then it unfurled itself in this like delicately orchestrated dance once it was in space without human involvement. So like very expensive to figure that part out, especially.
And the fact that it didn't fail is also a big win for us.
Yes. Yeah, I'll tell you.
Because God knows how many things we've launched into space and we're like, well, it didn't work the way we were hoping it would.
Right. Like Hubble.
Yeah.
Like we had to fix Hubble after it was launched. We could not fix JWST in this way. So I know for a fact that after it launched in 2021, there were still like several months before it reached its location, and people were stressed.
Yeah,
There's
like
months of stress streams of it not unfolding properly, and then $9 billion in the toilet. Yep.
That feels like a analogy that I don't want to think too hard about.
Yeah. So that's the most expensive. The wackiest, and I think one of the cheapest, is perhaps why it's so wacky, but the wackiest is it's called the Bustling Universe Radio Survey Telescope in Taiwan, or BURST.
I was like trying to spell that out in my head as you were going. I'm like, okay, this is going to be something fun.
Something fun. BURST, because you have to do the double T, is 256 antennae arranged in an array, like pretty close together. If you look up a picture, Julia, of the BURST telescope.
Look it up right now.
Yeah.
Don't forget the 2 T's.
Yeah, you can. It's scheduled to come online in the next few months, and it really just looks like a bunch of like bunny ear antennae in a field.
Wow, it really does.
Yeah,
it just looks like
really
that. Huh?
So it doesn't have a dish. There are no mirrors. There are no lenses. There's no glass at all. It's just metal and wires. And the idea is that they can make a really cheap and fast to produce telescope array for the brightest, most energetic events in the universe. Like that's all they'll be able to capture there. Because notice, they don't actually really have a telescope. Like, they don't have a big thing that is collecting photons. So they're just going to be hit by the brightest and most energetic photons that happen to come by them. And so they are specifically looking for these big events like fast radio bursts. We discovered them in the early 2000s, I want to say like 2007. And since then, we've detected about 1,000 of these really strong bursts of radio light. And we don't know exactly where they're coming from or how they work. And so we're trying to come up with cheap and fast ways to study them. And the burst telescope will let us do that.
I love when any sort of person who is much more knowledgeable than me in science, especially when scientists are like, yeah, we just like don't know where it's coming from. I'm like, okay, so this is the beginning of that sci-fi horror movie that I'm picturing in my mind. And I'm really excited about that future.
Great. Julia, I promise I will let you know if we discover that fast radio bursts or like gamma ray bursts are aliens coming at us.
Yes, I want to know that immediately.
So, Julia, you now know a lot more about telescopes, hopefully, than you did 50 minutes ago. Do you feel like you know enough to make your own?
With a little help, probably.
Yeah. Okay, great. I'll be here for you. I have a series of questions, and don't feel the need to make it science-y because that's my job. Your job is to give me the ideas.
Okay,
great.
Cool. Got it.
All right, so for our build a telescope, you first get to choose what event or object or phenomenon are you curious about? Like, what do you really want to study?
I really want to study planet surfaces.
Okay. Yeah.
Okay.
Planet surfaces. Okay, that's good. Okay, great.
I know we have like, rovers and stuff that we've done that for other planets and everything, but I want to dig deeper, or at least I want the full picture of it. Do
you want it to be a specific planet or a survey of planets?
A survey of planets.
Okay, cool.
Because then I don't have to pick.
Yes. Yeah, pick. Very Libra of you.
Mm-hmm. Very indecisive.
Okay, what wavelength are you trying to observe in? I can
what are
tell
my
you,
options?
Yes. So we here on Earth, we see in the optical, that's like kind of in the middle. Below that, we have infrared, where you can start seeing like dust and through a lot of dust and gas. Then we have the microwave, where you can see a lot of like cosmology stuff. We have then the radio waves. Those are the longest waves, and you can see a lot with radio. Radio is my favorite region. Okay. Going up above the like more energetic than visual, we have the ultraviolet rays, we have the X-rays, and then we have the gamma rays, which might turn people into superheroes.
I was like the Hulk. Got it.
Hulk,
cool.
Yeah.
I actually think that infrarays might be interesting because like what I always find interesting in sci-fi, and I don't know how much of this is true for actual science, is I always like this idea of, yes, this planet has like a very stormy atmosphere, or like there is some sort of like gas that we can't pierce through with optical. And so we want to see what is past that and like the true actual surface of the planet. Like I think that's true of Jupiter probably, and a lot of the gas giants.
Yeah, they have that swirling stuff so you can't see what's underneath easily.
Yeah. I want to see what's underneath.
Ooh, yay. Okay. I like also using an infrared mission here because infrared is really like letting you see heat signatures.
Cool.
And so as the planet rotates and it collects some heat from its star, we might be able to do something fancy as it like turns to the night side and the heat from the day side is cooling off. We might be able to like do something there where we can look at the differences between the night and the day side and like subtract that to figure out what the surface looks like.
Yeah. And also in my mind, I'm like, well, what objects on the planet are retaining heat, going into the nighttime and everything like that. So,
yeah. Okay. All right. I love this.
I want to find aliens. This is what the answer to this is going to be, but I want to find aliens.
Great. And, with an infrared planet-based mission, you're also like priming yourselves well to find things like Dyson spheres and other megastructures that are emitting their own heat because they're like technology.
True. Okay, I'm excited. Great.
Yay. All right, so we're doing an infrared planet finding or planet studying mission. What size do you want it to be? How big do you want it to be?
I want one of those rich guys in the 1900s style observation places.
Okay, so we're thinking Earth-based.
Yeah, well, I am, but I guess that, remember, I didn't realize we could send telescopes into space until about 30 minutes ago.
Okay, well, now that you know we can, would you rather have this telescope on Earth or up in space?
Well, I guess up in space would get me more information. I like the romanticism of being able to look into my microscope while on Earth, but because we're not doing optical, it would make more sense for it to be in space actually doing this survey of planets. So
why do you think you get more information when it's up in space? I'm not saying you're wrong. I'm just curious about your thought process.
I guess because you are closer. And I think also because we were talking earlier too about the magnetic fields and this idea of like you have to be closer to the object in order to read magnetic fields. I know we're not doing magnetic readings with the telescope that I'm describing, but I don't know.
You get closer. Yeah. Interesting. Yeah. So the advantages of going up in space are that you're above the atmosphere, so you're not dealing with any sort of atmospheric aberration from the water vapor and stuff moving around. And especially in some wavelengths like ultraviolet, which don't really get through our atmosphere, you have to be above the atmosphere to read it.
Also, my immediate response was you said like, yeah, because of the water particles and everything like that. I'm like, yeah, because if it's cloudy, you can't see the sky.
Yes.
Yeah.
Yes.
I was like,
actually.
Yeah, because clouds. Got it. Right.
No, but I'm glad you got there. This is why when you are on Earth for a telescope, you usually put them like high on a mountain. Right. Because you're above most of the atmosphere. But the other advantage you get from being in space is that if you plan your orbit right, you don't have to deal with like daytime.
Right. Like we were talking about.
You can always face away from the sun, yeah.
There we go, where you don't have to worry about the planet keeps orbiting for you. You can just be in the orbit of the planet.
Okay.
Cool.
So a space-based telescope, which means it's really expensive to send stuff up and size is a little bit of a limit. But you specifically said like rich guy. We're talking robber baron funding here.
We're talking Vanderbilt estates.
Yeah. Money is no object. Okay. So it's a space-based infrared telescope. How big do you want it to be?
How big are the space-based ones typically?
That's a great question. So Kepler... The Kepler Space Telescope, which did study planets, but more in the optical, that was, I want to say, 1 meters across.
Okay.
So several feet.
That sounds correct to me. I would assume so. That feels right. So when we're describing that is the lens, right?
Yeah, that's the diameter of the mirror at the...
Gotcha. How big is the actual, probe it's on typically then?
Ooh, yeah, like the whole payload.
Mm-hmm.
I want to say Kepler was bus Some of them are bus-sized.
Okay.
Yeah.
I'm just trying to picture it in my brain, so I'm going to pull up an image for my own edification.
Yeah. Kepler looks like a little tube of lipstick, which I love. Mm-hmm. JWST was really big because it had it had that whole big shield that it had to fold up.
Right.
But yeah, they can get pretty hefty.
Oh, okay. He does look like a little tube of lipstick. I love that.
Yeah.
That's adorable. Okay, fantastic. Thank you. I was just like, I wonder how big it is.
So something like Kepler-sized.
Yeah, I think so.
That's nice.
I like the style of it too.
It is. Yeah, it's good. Has a good 90s, early 2000s aesthetic, I think.
Mm-hmm. There's something about that, the gold foil of it, of the space stuff, that I'm like, yeah.
Love the gold
nice.
foil look.
That's good stuff.
Yeah. It tells you exactly what's happening.
Yep.
Okay, so our wavelength is a little bit bigger than Kepler's. And if we keep the same size, that means our angular resolution, remember from earlier, our angular resolution will be a little bit worse than Kepler's.
Okay.
I think, since we're especially trying to look at the surfaces of planets, we want really good angular resolution. So I would make it bigger.
Okay.
Yeah.
So maybe, I'm I don't know, do we double it in size?
Yeah. Let's at least double it. I'm saying I want a 10-foot.
Gotcha.
I want a 10-foot infrared space-based planet hunting mission.
All right. I'm into it. I like it.
Great. What instruments are we putting on this thing?
I think we should have a visualizer, is the thing that you said earlier. I think we should definitely have an imager for sure. And I don't know what it is that reads the infrared, but I think we should definitely do that since we're going to be doing it.
Yeah, just like a camera or an imager that is like tuned to the infrared. Yeah.
Yes,
and we could even do it. We can have a couple imagers on it that are tuned to like slightly different wavelengths so that we are basically seeing it in two different colors so we can compare and contrast.
Yes. And also that'll make a great image when you kind of like superimpose them on each other. And now you have depth, like 3D glasses.
Oh, I love it. So let's do like a near infrared and then a far infrared.
Ooh, okay.
Imager. Yeah.
I like that. I like the whole spectrum of infrared. I'm down for it.
Speaking of spectrum, I do think we should have a spectrometer.
Sure.
There's this really beautiful technique, I love it so much, called transmission spectroscopy, where you can study the elements in a planet's atmosphere by seeing like how the light from its star is affected as it passes through the planet's atmosphere.
Yeah.
Or by looking in different wavelengths. Some wavelengths of light will pass through a medium but be stopped by another, just like how ultraviolet rays don't really pass through our atmosphere that well.
Right.
So if you were to look at Earth from outside in the ultraviolet, it would look pretty dark. It would look dark and big. It would look the size of our atmosphere. But if you were to look in the optical, you wouldn't see our atmosphere that much, so it would look smaller.
You would just kind of see our surface. Yes,
exactly. Yeah, so you can compare the sizes of the planet when you take pictures of it in different colors and start to see like how puffy its atmosphere is and what its atmosphere is made of. So like,
I'm glad you used the phrase puffy because I was like, can you see how? And then I was going to use the word thick. And I was like, maybe that's not the appropriate type of word for that to describe it.
No, but like I'm thinking, say that.
Yeah, listen, I'm thinking of like how humid it is when you're like, the air is so thick right now. So I guess I'm not too far off, hopefully, by describing it like that. But
not at all. I've genuinely had conversations with other astronomers discussing atmospheres where we're like, yeah, that planet is like 3 C's thick.
I was hoping you would say that, but I was like, don't get your hopes up, Julia. I'm sure that's not a real thing.
I'm here to make all your hopes come true.
Yay!
Okay, so we have at least 2 imagers. We have a spectrometer. I think we can give it like maybe another spectrometer and then some sort of like guidance thing so that it's pointing in the right position. And that's probably as many instruments as we're going to put up.
Yeah, I was going to say, how many can we get up there? Because like now I feel like we're pushing the envelope a little bit.
Yeah. The standard is like from 3 to like 8, I think I've seen on a space-based telescope.
And I think it makes sense to make sure that you can control what it's looking at. That does check out for me.
Yes. Yeah.
Incredible.
And then the final question, Julia. What should we call this telescope?
Oh, now this is fun. Because you know me, mythology nerd. I feel like we've used so many of the good mythology names on like the planets and the moons and stuff like that that it makes it tough. Oh, I have a good one if we were doing the sun, but we're not doing the sun. I'll tell you my favorite if you want for a sun-based mission. Yeah. Do you know the story of Cleite?
No.
Cleite was a nymph that was in love with Apollo, but Apollo did not return her advances. And so she kind of laid out in the field and would watch the sun go by until she wasted away. And so Apollo turned her into a sunflower.
Oh.
So that's a kind of nice one for a sun-based mission, but not what we're doing
Not what we're doing. I think there's a good opportunity here to like venture outside of Greek myths if you want.
I want to do something related to like travelers, perhaps, because we're doing a multiple planet sort of mission. Ganesha is always a good one. I feel like as a god of thresholds and like new beginnings, but also like a god of literally success, like starting successful new ventures. Like Ganesha is a good option potentially.
Oh, I love that.
Yeah, I think we could go with that one. There's some good like Mayan and Aztec ones about like commerce and traveling merchants particularly, but I'm feeling this one. I also want to give a shout out to Khonshu, who is a moon god, but also is like specifically a Egyptian god who watches over travelers who travel at night. So if we were doing more moon-based ones, I guess. I don't know. I don't know. Right. There's so many good options.
I know. This is the hard thing about being a folklorist. Like, there's just so much good stuff. I think Ganesha is a great name for this.
Cool.
We're also definitely going to like incorporate that into the design For sure.
Yes.
Like if you think we're not going to have, because some of these old telescopes, especially the ones from the 70s, they had such a 70s aesthetic, and sometimes you would see like this long arm of instruments coming off of the main body of the thing. And that, like I want this telescope to have a trunk now.
Yeah. No, I love that. Or like some sort of fins that kind of resemble elephant ears.
Yes.
I think that would be pretty cool.
Yes, Julia. We didn't decide like what type of orbit it has, but I know like Kepler had some sun shields. Like when it was facing away from the sun, it had shields on its back. So yes, ear-shaped sun shields for sure.
Kind of adorable. Kind of love that.
Oh my God, I love it so much.
Okay, cool.
Okay, fantastic. We built a telescope. It's called Ganesh, and it will launch in 2052 because that's how long it takes these things.
Yeah, and a solid $10 billion later, we're good to go. Yeah. I love the idea of those like folding out like origami, though, at the beginning of its mission.
So it will take $10 billion.
So it will $10 billion, yes.
Awesome. Julia, I've had so much fun here.
Me too.
Thank you for joining.
It was my pleasure.
Yay. I would love for you to brag about yourself. Like, what have you got going on? Where can people follow all of your amazing work online?
Oh, you can go to my website, which is very sparse, but it does have a link to a lot of the stuff I do, juliaschifini.com. You can check out Spirits, which is a boozy dive into mythology, legends, and folklore, where you can hear Dr. Moiya McTier on several episodes, I will say. You could also check out Join the Party, which is an actual play podcast. We're currently playing Masks in our new season, where we're playing teenage superheroes in superhero high school.
So
and
good.
I play absolute stoner of a Frankenstein's monster character. She's great. I love her. Her name's Shelley Craft. And
you're also creative. It makes me so happy.
And you can check out if you like science fiction, I've edited and sound designed a bunch of different science fiction shows, including Janus Descending and Primordial Deep. So if you like a spooky science fiction creature feature, those are both great shows to check out.
Especially as we're heading into the spooky season, friends.
Yeah, absolutely.
I love it. Thank you so much, Julia. This has been a treat. I really want Ganesh to be a real telescope now.
Oh, I'm sorry to put it into the universe and not be able to make it myself.
Wait, but Julia, remember, we have changed the rules of the universe so that we can make or destroy anything we want if we just believe it hard enough.
Yeah.
So Ganesh will be real.
Put it out there into the universe. Yeah. We can make it happen.
Yeah, listeners, if you all think about it hard enough, we can make this a reality.
Let's change reality, baby.
Well, no matter how solid your reality is, you are space. Pale Blue Pod is hosted by me, Dr. Moiya McTier, a.k.a. the universe's bestie. I created the show with original co-host Corinne Caputo, a comedienne extraordinaire, and help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen, and our audio editing is handled by the incomparable Misha Stanton. I am Go Astro Mo everywhere online, and you can stay in touch with the show and the universe by following Pale Blue Pod on Instagram or checking out our website, palebluepod.com. We are a member of Multitude, an independent podcast collective and production studio. So if you like Pale Blue Pod, you will love the other shows that live at multitude.productions. And if you want a shout out on the show and research notes for every episode, you can join our community over at patreon.com/palebluepod for just about $1 per episode. Thank you so much for listening to Pale Blue Pod. I'll be back next week. Bye.